دكتور ما نسمعك، مسوي ميوت.
الدكتور ميوت.
Sorry for that. أنا كنت أشرح من ساعة عشان let us see. You can hear me now, right?
اي دكتور.
اوكي دكتور احنا اوكي.
I was just saying that last time we talked about the mechanical properties of the different phases and why we were doing that, because basically we covered how to produce different microstructures using different heat treatments. We could do that easily now using the phase diagram and using the TTT diagram. Then, well, since we know there is a strong correlation between microstructure, as you know, the pillars of the material science and engineering, structure and properties, they are linked together. So there is a strong correlation between microstructure and mechanical properties. So if we know what the mechanical properties of the different phases are, so it will be easy then to design the material that you want using the different heat treatments to produce microstructures with profound mechanical properties. So we dealt with the different phases so far. Last time we talked about the bayanite as they exhibit a desirable combination of strength and ductility. Today will be the last phase we are going to deal with, which is the martensite phase. Martensite is the hardest and the strongest microstructure for a given alloy, a steel alloy. It is the most brittle phase of a steel. It exhibits nearly negligible ductility, negligible plastic deformation. Of course, we explained where that high strength and hardness is coming from, and brittleness of martensite is due to the carbon atoms which are trapped in the BCC crystal structure, and which makes a solid solution. What type of solid solution? That is a interstitial solid solution, and that is because these atoms are trapped there, cause the stuffing, actually, which we said stuffing of the BCC crystal structure, causing it to increase in size, elongate, and twist as well. And it's like stuffed, as we said last time, and it produces actually solid solution strengthening as well, which is basically interstitial solid solution. And it is not due to the microstructure, as was the case in the perlitic structure or bayonetic structure or spheroidite that we talked about. Also, austenite is slightly denser than the martensite. Therefore, during the phase transformation, there is a net volume increase. That volume increase, we said, happens going from the BCC crystal structure. And instead of the FCC going to the BCC crystal structure, we said, it gets transformed into a BCT crystal structure instead, and that is longer. It is twisted as well. So this is where we are talking about the net increase in the volume that we have. In addition to that, there is also a problem actually that we could have in producing the martensitic structure. Large pieces that are rapidly quenched may crack, or as a result of internal stresses, or even if they don't crack, there will be internal stresses, or what we refer to as residual stresses, happening in the material. And why does that happen? That happens due to the non-homogeneous cooling. Meaning what? Yani when you have for example, a material due to the non-homogeneous cooling, why does this non-homogeneous cooling cause these internal stresses in the material? If you have a surface of the material, so the material has a certain thickness, and draw it big, so the material has a certain thickness there. If let's say this part of the material has let's say, low temperature, and that part of the material has high temperature. If there is an ingredient in the when you are when the material is solidifying, for example, when there is a difference in the material temperature, this is temperature T1, for example, and that is temperature T2. That difference in the temperature, basically, between outer side and inner side, let's say, causes the development of internal stresses, which we refer to as thermal stress. So sigma T, that's called the thermal stress, is equal to, there is an equation that you will be covering in your mechanics course, MEMG 370. So it has some values there. I'm not concerned with all that. I'm concerned with the delta T. That delta T, which is equal to T2 minus T1, the higher temperature minus the lower temperature. The higher the temperature ingredient, the higher the thermal stress, which is actually an internal stress which happens in the material there. So that internal stress, if this internal residual يعني ساكنة, okay, this is what it means. That residual or internal stress which happens here, if this internal stress, let's say, or in this case, let's call it the thermal stress, is bigger than the tau, let's say sigma in shear. I want the shear stress, okay, bigger than the shear modulus, shear yield strength, like that. If this is bigger than that, the material is going to crack. Examples of which, for example, happen when you are in winter season, for example, and you are having a mug or a glass for tea. You go and wash your glass there in the water tap, for example, بالحنفية مال الماء، تروح تغسله بماء بارد, and then you come and put the tea in it. The tea is nearly at 100 degrees centigrade. What happens in a lot of times there, this glass cracks. Why? The internal temperature, which is nearly 100 degrees centigrade. The external temperature is basically, let's say with cold water, it could be 10 degrees centigrade or 5 degrees centigrade. It causes an internal stress in the material which is higher than the yield stress, shear yield stress, which causes the breaking of the material. So this can cause fracture of the material or cracks in the material. And even if it does not cause that, in the metals there will be an internal stress or residual stress which develop in the material and stay there. If this happens, then we have a problem, because the material would not really be good to use. Why? It loses its full capacity as a material to be stressed. So there is an internal stress, there is a residual stress, and then if I apply another load, both loads will be acting there, so the load carrying capacity of the material reduces. So this is a problem when we have specifically when we have large pieces being quenched, basically, because when you quench large pieces, then there will be a difference between the internal temperature and the external temperature there. So there will be a temperature ingredient in between. Large ingredients that causes these internal stresses to develop or the cracks to happen in the material. So what is the solution for this? We're going to go through this during the lecture. So to talk more about the Martensite mechanical properties, we can compare the fine perlite versus the Martensite mechanical properties. For example, for the hardness, Brinell hardness, you can see there, with increasing the weight percentage of carbon, the carbon content in the material. As you can see, the Martensite has very, very high hardness compared to the harder fine perlite, not the coarse. The coarse is even has softer hardness there. This is the harder or the stronger perlite. You can see there is a big difference between the hardness between the martensite there and the perlite, the fine perlite that we have here. So therefore we know fine perlite has much less hardness than the martensite. The strength also the same. Actually, normally also compare. I mean, this is another figure which is the same figure that we are having here. We are comparing the fine perlite and the martensite, but we are also showing here what we refer to as tempered martensite, tempered at 371 degrees centigrade. We are getting that behavior. What is tempered martensite? Well, basically, the martensite itself as a 100% phase is not actually usable because it has negligible ductility. Forming of that material is very difficult. You cannot be forming it. You can. It has that brittleness, and the material makes it non-usable actually in practice. So that's why we do something called tempering of martensite in order to make it less brittle and more ductile with high strength, which makes some application to this martensitic structure that we have. So this is how we can make use of the martensite, basically either make part of it or aggregates of it in the material, or as a whole temper the martensite and make it with less strength, less hardness, but more ductile material, which could be used in industry. What is tempering? What is tempered martensite? You see, this is what I'm saying. As a quenched pure martensite is very hard and brittle and cannot be used for most applications there. Tempering is a heat treatment that we do, and this heat treatment that we do actually, if we look at the phase diagram here, we basically, of course, this is starting at 400 degrees centigrade. If we go to 0 degrees centigrade, we'll go a little down there. So we basically, what we do in tempering, we raise the temperature of the martensitic structure from 200 or 250, we can go up to 200, from 200 to 670, 675 degrees centigrade, some temperature there. So if we increase the temperature of the martensite and keep it for some time for heat treatment and khali, for soaking, what is going to happen? What do you expect to happen there? You remember when we said that the martensitic structure, what is the martensite structure? It has a BCT crystal structure. Why? Because the carbon atoms in different sites actually got trapped in the BCC crystal structure, causing the crystal structure to elongate. But not only elongate, also it will be some twisting to the material will happen as well at the same time. Now, this elongated crystal structure with the trapped carbon atoms, when you raise the temperature, and we said that the martensite is a metastable structure, metastable, which means what? If you increase the temperature, what is going to happen? The distances between these atoms of iron are going to become bigger at higher temperature. Tabi'i, the distances will become bigger, and these carbon atoms, what will happen to them? The carbon atoms are going to be allowed to diffuse out. They are going to be allowed to diffuse out. The carbon atoms will come out. Why? You are raising the temperature now, and you are energizing. You are giving energy to the carbon atoms, and you are making the distances between those iron atoms bigger, so you are allowing them to escape now. Once you allow that, these carbon atoms in the steel are going to go and form the cementite basically phase, because there will be high carbon content. They gather together, the carbon atoms, and they form the cementite phase. This is what happens if you go and and this is why you need to understand, and we explained that before, that the martensite is a metastable phase. As you can see, if you And we said that you cannot be using the martensite in high temperature applications because of this, because it's going to change its structure. If it changes the structure, then this means that we have a change in mechanical properties. So basically, we are changing now the crystal structure of the material. We are changing the property of the material. The phase is going to change because of this diffusion. So the atoms are going to diffuse. The carbon atoms, they are trapped there, but they are allowed to escape, and they form the cementite phase in the material. Tempering is a heat treatment that improves the ductility and toughness of the martensite. So this is what the main aim actually is that, but in addition to that, it relieves internal stresses produced during the quenching. So this is also a solution to the internal stresses, as we have talked here. Large pieces could lead to, internal stresses or cracking to the specimen. The heat treatment here cause what? If there are any internal stresses, the atoms are going to redistribute and anneal out. This is what the phrase that we use. They anneal out the internal stresses in the material. We get rid of the internal stresses in the material. Procedure is accomplished by heating. Tempering procedure is accomplished by heating the steel to a temperature below the eutectoid temperature for a specific time, and that time also influences the tempering, the behavior of the material. Normally, the tempering happens or is done between 250 to 650 degrees centigrade. From 250 down there up to 650 degrees centigrade. Sometimes we go also to 675 degrees centigrade. Does the temperature at where the tempering is done affect the microstructure? Of course it does. Does the time that we let the material soak, does it affect the crystal structure? It does, of course. Let us look at that as well. So what happens in that transformation? When we raise the temperature, when we raise the temperature of the martensite and keep it, let's say, at 375 degrees centigrade or 400 or 500, whatever, the carbon atoms are going to escape, and the BCT crystal structure is going to change. Here, the BCT single phase is going to change. It will become back, to a BCC crystal structure, which is alpha, and the carbon atoms which are released form the compound, the cementite in the material. So you again have this two-phase microstructure, like the perlite, like the spheroidite, like the bayanite as well. But and this microstructure, the tempered microstructure which forms, has a microstructure very similar to the spheroidite, which we refer to as spherical cementite particles in a matrix of ferrite. But the cementite particles is much, much smaller than the spheroidite. The spheroidite sizes are much bigger. This much smaller size of particles there causes the development of much more. Yani if you have, this is the microstructure, and you have, let's say, these are the particles of the cementite there, okay? Or the other case, in the tempered martensite, you have much smaller, basically, particles like this, okay? Much more, with the same volume fraction, actually, we could say, okay? We will have much more there. And then, imagining we have the same volume fraction, the size, the proportion of these actually is the same as the proportion of those. Which one will be stronger? The finer will have much stronger properties than the coarse. This is the spheroidite. This is the tempered martensite. Why? Because the grain boundary and the second phase boundaries here, when it is very fine, is much greater than the second phase boundaries here. The phase boundary due to these four are actually only that area and this area and this area and this area. On the other hand, for these, it's the area surrounding any of these spots, the smallest spots. Adding them together will be much greater than that. So they will have much greater resistance to dislocation movement than those. and that's why the material behaves much stronger. And this is what I'm saying. Smaller size of the particles will make more phase boundary area and more strengthening effect to the material, and that's why tempered martensite are much stronger, even stronger than the fine perlitic structure. Another thing, how we will affect the tempering, that the behavior or the mechanical properties of the tempered martensite. We say the higher the tempering temperature, the larger the particle size, the lesser the strength. So you can also control your tempered martensite with this the tempering temperature that you are using. If we go and temper at high temperature here, let's say comparing with high temperature or at low temperature, let's say at this is 400, let's suppose we are below that. I don't want to go below. Let's say this is at 250 and that is at 600 degrees centigrade. Will there be any difference between the material produced in each case? And definitely there will be. When we take the temperature to 600 degrees centigrade and keep it for some time like that, what is going to happen? That microstructure basically will, for the same reason that we said how the spheroidite forms, remember? It's going to form the tempered martensite, but since we have the material for some time at high temperature, the material will behave coarser. So you will have a coarse it's not as coarse as spheroidite, but we say coarse tempered martensite. But when we are at lower temperature, these will be finer microstructure. The finer the microstructure of the tempered martensite, the stronger they are. And this is what we are showing here. As you can see here, the tempering, this is the tensile strength and the yield strength of the material. That's the yield strength. This is the tensile strength of the material, and this is the ductility of the material in terms of percent elongation. Those are drawn versus the tempering temperature. So when you are tempering, because the least we do is we go to 200. That's the least. Normally we go to 200 or higher. So if you go to 200 degrees centigrade or 400, let's say, I mean in between is drawn also the curve, and 400, 500, 600, the lower the temperature are, the less the ductility and the higher the yield strength and the tensile strength, as you can see. As you increase the tempering temperature, you have an increase in the ductility and you have reduction in the strength, yield strength and the tensile strength of the material. So this is what we have already because as you go higher with tempering temperature, the coarser the material will be. The coarser the material, this means less strength and higher ductility, as it is shown in this figure as well. The shape of the this heat treatment, which is tempering the martensite, reduces the brittleness of the martensite and reduces also the internal stress caused by the quenching that we normally do in producing the martensitic structure. The martensite, tempered martensite, look like this. You have a spherical microstructure which looks very similar to the spheroidite phase, but and these are surrounded by the in this case we have the black here, which is the ferrite phase. It's much finer than the spheroidite phase. So this is the tempering. Inside the process of doing that, the heat treatment, normally the heat treatment cycle that we normally use in order to do that is that we raise the temperature, let's say, to the austenization temperature, that we raise the temperature to be in the austenite zone, basically. Okay, we are somewhere here, and then we quench from the austenite to room temperature to produce, from the 900 degrees centigrade, or it's not necessarily 500 or 900, of course. It depends on the composition of carbon and the temperature you are at in order to make to be in the austenite zone. So once we heat a treat from that, then we quench. That is the quenching, very fast cooling, and we produce the martensitic structure here. Once we do that, then we start with the tempering. That, let's say this is at 200, this is the least temperature, which is the tempering of the martensite. When we produce, let's say 100% martensite here, then we temper, we raise the temperature to 200 degrees centigrade and keep it for some time, and then cool again. This produces the tempered martensite. Of course, that temperature, as we said, 200, 300, 400, 500, 600, it changes the microstructure of tempered martensite and changes mechanical properties. Not only that, but even the soaking time from here to there. How much do you keep that also affects the microstructure of the material. That's another issue we don't want to go into. But there are different variables that you can control, basically, based on research that you could do in order to control the microstructure. As received. Yes.
Can we get something from this?
If you have a question, just wait. Let me finish this slide. I'll come back to you. So this is the as received microstructure. As you could see there, as received. This is the microstructure before we do anything. Once you quench, basically, from the 900 degree, from the austenite zone, you get the 100% martensite structure there. You can see the lathe martensite very clearly. And then if you do the tempering, you change the microstructure to this very fine spherical dispersion of the cementite in the matrix of the ferrite. Tell me.
Doctor, can we make a process like the vice versa for this quenching, like going from the martensite till the austenite?
Going from the martensite to the austenite, you can do, but it's not the opposite process, if you mean that. When you heat a treat, let's go to the phase diagram. Okay. When you are somewhere, anywhere here, you just heat up the, if you have martensite, or you have not only martensite, if you have any phase, if you have perlite, if you have whatever phase you have, if you raise the temperature and go in the austenite zone, you are there somewhere, you will get the austenite phase. Clear?
Clear.
So this is what we already did. If we want to also compare now mechanical properties of the quenched and tempered steel, so you quench and tempered, you have tempering. Basically, if you want to get the tempered martensite, of course you have to quench beforehand. We compare the normalized perlite steel and the quench and tempered steel. You are comparing those two. So you can see here, this is the normalized perlite. Normalized means that you are using slow. Let's see. Here, so if you are heat treating slowly, as we said, you are going to the perlite zone. That's the perlite zone. If your heat treatment is moderately, you avoid the nose of the TTT diagram and you fall into there, and then you heat treat, you are going to form the bayanite phase. Of course, this is a small jump in temperature. You could have a bigger jump in temperature to produce another microstructure. As your delta T is bigger, you will be producing the fine perlite here, right? And on the upper temperature, with the smaller delta T, you will be forming the coarse. It's recorded, so I don't need to write. But anyways, you will produce the coarse perlite, and the same thing for the bayanite as well. You could be producing with that delta T or this delta T. You have the upper bayanite and you have the lower bayanite. The upper bainite, of course, is coarser than the lower bainite, and so on and so forth. For the martensite, you jump with the temperature there to temperatures below the room, at the room temperature, to produce the martensitic structure there. This is what we are saying. So in the case of perlite, you are having slow you could call that normalizing, yani leaving it to cool slowly. You will be producing the perlitic structure here. And going back to what we were saying here. Normalized, this is what we mean by normalized perlite. That means that the cooling that we are doing is slowly. As you could see, the behavior with increasing the carbon content, we're looking at the strength in megapascals, with increasing the carbon content of the steel. What is the behavior? You could see the range between the yield strength and ultimate strength. It increases basically, and this is what happens to the ductility in general. The fracture strain, this is what is taken to measure the ductility here. You could see it happening like that. When we compare that for the same curve, actually, weight percentage of carbon and the strength in megapascal, for the quench and temper, which we can refer to this as the tempered martensite. With increasing carbon content, you could see the yield strength and the ultimate strength of the material is much bigger than the normalized perlite. And not only that, the strength, the yield strength and ultimate strength are much bigger, but also you could see actually the ductility with no loss in the ductility as well. The material is also having high appreciable ductility as well, which you can utilize in making different forming processes as well using the tempered martensite material. The quenching of martensite, we said it causes sometimes, if the large pieces are considered, it causes the cracking of the material. But also, even if it does not cause a cracking, it will cause internal stresses in the material. One solution to resolve the problem of cracking or internal or residual stresses happening in the material was the tempering, because they anneal out any internal stresses in the material, if there are any. So another solution to that as well is alloying for the steel. Alloying slows the diffusion control phase transformation of the steel. Basically, if we add a chromium and molybdenum to the steel, basically what it does, if this is our TTT diagram which we are talking about, what it does is that it pushes the TTT diagram actually to the side. Yani when we draw the TTT diagram, we will see that it is pushed to the side, making more gap of the nose of the TTT diagram. If you have more gap there, this means that you have more time to produce martensite. You don't have to quench it that fast. You can use less time, and less time, less or more time, leaving more time for transformation to occur. This means that you will be having less internal stresses due to that. So when you push that down, actually, the effect of alloying with chromium and molybdenum, it pushes 1% transformation in the alloy. So which causes that you have much more plenty of time there in order to produce the martensitic structure, which is a way also to reduce the internal stresses in the quenched martensitic structures there. So you could do it by tempering, and you could be doing it by alloying as well. Both normally people do in order to reduce the cracking or the internal stresses developing in the material. In summary, the processes that we use in order to do the heat treatments there and produce different microstructures. The austenite phase is normally, if it is slowly cooled, what happens when it is slowly cooled, basically, when it is slowly cooled, this means that we could use the phase diagram. When it is slowly cooled, either you are producing from the austenite zone, you are producing the perlitic structure, the alpha plus the cementoid, or you are producing a pro-eutectoid microstructure and then the eutectoid microstructure, and this is what we are saying here. So if you do slow cooling, you will produce perlite, the alpha plus the cementite layer, plus a pro-eutectoid phase. This pro-eutectoid phase could be the alpha prime that you produce there, or it could be the cementite prime, let's say, pro-eutectoid cementite, which develops if you are cooling from that area. If we are looking at the development of microstructure of the eutectoid microstructures there. And if we moderately cool, not slowly cool, if we moderately cool, and when we say moderately cool, so we don't use the speed, or we don't stick to the condition of using the phase diagram. This means that our heat treatment, our cooling rate is high, that the phase diagram cannot then predict for us what microstructure will develop, and that is in the slow cooling. Of course, you are doing that. But in moderately cooling, so you avoid the nose of the TDD diagram, and you will be producing the bayanite phase basically. So moderately cooling, you cannot refer to the phase diagram because this beta is a metastable phase. It's not available here, as you could see here. It's available only there because condition for the phase diagram. So you will produce the bayanite, and the bayanite consists of plates of the alpha phase ferrite and needles basically of the cementite phase that you have. So plates and needles, that is the bayanite phase that you will produce. And if you do rapid cooling, rapid quenching, or quenching if you want, so you do the quenching, you reduce the temperature very fast there, you will be falling in the martensitic structure. The martensite has a BCT phase, and it is diffusionless transformation. It does not happen by diffusion. You are actually not allowing the diffusion of the atoms in order to produce the martensite. You are suppressing the diffusion. Suppressing يعني تعطل. Why? With this very fast cooling or quenching, you suppress the diffusion process and trap the carbon atoms inside the BCC crystal structure. But since it cannot accommodate that much carbon atoms there, it causes, the twisting and the elongation of the BCC crystal structure, forming that BCT crystal structure there. And if you reheat that, and as we know, that is a metastable phase, and that's why we said, and when we dealt with the martensite phase, we said, and the metastable phases in general, that you cannot use them in high temperature applications there. So if you reheat that, this is going to transform. The BCT crystal structure is going to become bigger. The carbon atoms will be allowed to, or will be released basically, and will move out. The crystal structure again changes to BCC crystal structure, which is the alpha phase, and the carbon atoms go and form this very fine cementite particles in the material, which we refer to as tempered martensite. In terms of a strength of the material of these different phases that we dealt with so far in chapter 9 and chapter 10, you can see, and you can add also ferrite here if you want. Better to add the ferrite here because ferrite is one of the phases also. The ferrite phase. So you can say ferrite is the softest actually phase of the steel. Then after that, and if you go in this direction, as if the strength of the material of the phases increases basically. Ferrite is the softest, then comes the spheroidite, then comes the coarse perlite, then you have the fine perlite, then the bayanite, then the tempered martensite, then the martensite. Okay, so as you go in this direction, you have higher strength and higher hardness as well at the same time. And as you go down there, you have more ductility, as you could see there. with the direction of the arrow which we are showing here. With this, we are ending chapter 10 basically, and ending the material course for the material science and engineering for this semester as well. Any questions, guys? Any questions, guys?
Doctor, on the question of chapter 9.
Yes.
Why laminar configuration develop?
Why again?
Laminar configuration develop.
Why the lamellar configuration develop? The lamellar configuration, well, we don't have the figures here, but okay. Before we do that, does anybody have any question with regard to today's lecture? شنو اسمك انت؟
رياض.
Riyadh. Before we do that, does anybody have any question with regard to today's lecture?
No.
No questions there. How many students are attending? Not much. What is this? I need to open that to show you a figure in chapter 9 as well to answer the question. Although we have some figure there, I need to also show you a figure to explain or see it. Yeah. Well, lamellar configuration, we explained it here, if you remember, for this case, all right, where we dealt with the eutectic microstructure, if you remember, right? In this case, we explained it, and we explained it also another time when we dealt with the iron carbon phase diagram there as well. Where is that? Yeah, here. We explained that actually 2 times. But anyways, there is no harm of explaining again. Just for you to understand that we are looking at, we are looking at the same explanation here or there as well. Or there as well. We are explaining what's happening in the development of the if you want the eutectoid or the eutectic as well. It's the same explanation that we're having here. In the eutectic, and the eutectic is also there in the iron carbon system as well. As you could see here, if we are coming down with the temperature, and due to that this is a eutectic point, the melting or solidification occurs across a point. Let me make this longer. The melting or solidification occurs across a point only. So this liquid basically needs to go from the liquid phase to 2 different solid phases, the alpha solid solution and beta solid solution. They need to go from a single liquid phase to 2 different solid phases. Not only that, but it needs to do that change to 2 solid phases which have drastically different compositions of carbon as well, because once you are below that, you have the alpha with 18.3% by weight 10, and the beta which has 97.8% by weight 10. So it not only requires to change the liquid phase to 2 solid phases, but to 2 solid phases with drastically different compositions as well. So how can it do that fast transformation? Because it is across a point. What the material does, is that light which I explained, the cleaner, what he would do when he did not do his job and the janitor, the supervisor came. If he is in a corridor, he pushes the dirt, actually the dust, to the sides because it will not be clear. The material does the same. In order to do that process the fastest way, in the it will form the alpha phase, which alpha phase it has much lower tin in it. So in the alpha phase area, they push the tin to the sides, basically. And in the beta phase, they push the lead to the side. So you will develop a layer there of alpha, which is rich in lead, and on the sides of it will form the beta phase, which is low in lead but high in the tin, basically. This is what happens. And when we talked about the carbon here as well, you have the same thing as well. Since you have the transformation in the either in the eutectoid or the eutectic as well, same explanation go there as well. It needs to go from austenite phase into alpha plus the cementite. In this case, the alpha has very low carbon content, 0.0, that's the maximum amount, 0.022, while the cementite has very high concentration of carbon, which is 6.7. So what does it do actually? In order to do that fast transformation here, in order to occur, what it does is that it makes layers in the same way. Those layers develop in the same way that the carbon gets pushed to the side, basically, to form a nearly free carbon phase, which is the ferrite. And on the sides there, the carbon atoms gather together and they form the cementite phase, and that's why we develop this lamellar configuration. Clear?
Clear.
Any other questions, guys? No questions?
دكتور انا عندي سؤال
مم.
بس انه خارج موضوع الدرس يعني او المحاضره.
انزين بس خليني انا اقول شيء قبل ما نخلص. We are recording also, so we don't, since we are going to talk about that, we are going to stop this so that it is not. والله اقول لك خلي هذه يتسجل بعد. I already told you we have a final lab test. In the same time, we have the final test, so that people, when they see the lecture, they also hear this. If they did not so far, I sent you a message yesterday just to bear in mind that we have a final lab exam as well, as usually we do. That's number one. Number two, in terms of assignment, we did not get anything. I did not give you any assignment this semester. So in the syllabus, it has 5% basically there, and that 5% I'm going to transfer it to the lab marks. Lab marks, we're having 10%. That 5% assignment, which I did not give you to do, will go in the lab marks as well. So the lab mark will be 15%. The final is 40. The quizzes is 5. And we have exams are 40, which is 20% and 20 for the FISMA. So that's number one. Number two, I have asked you to submit a lab report, and I have asked you to submit a PowerPoint presentation, not the slide. Some people are just sending me the slide. I want you to present. I want to hear your presentation. That's a presentation. I don't want you to send the slide. To make a PowerPoint presentation recording, please, of what you are doing. Not just send me the slide. I mentioned that clearly now. Let me stop the recording so that we have a recording.